Okay, good evening, everybody. Today, what we're going to be doing, we're going to be going over two heap questions. How can we apply heaps to solve, in particular, finding the median at any given moment, or being able to sort K sorted linked lists into one big sorted list, dynamic doubly linked list. But first, what I'd like to do is I'd like to introduce a student who I've had for a couple of classes now, Samuel Battalio. He is a senior, and he did an internship at a company called Pure Storage out in Mountain View, California. So Sam has some really good perspective in terms of going through the interview process, but also for a lot of computer scientists, there's always a little bit of trepidation about what it's like out in California, particularly Mountain View, because any company in the shadow of Google. And so Sam's thrived in that environment. He has some really good perspective on that kind of stuff. So what I'm going to do is I'm going to turn the floor over to Sam. Is it getting a pin? Okay, cool. There's the pin. There we go. All right, so Sam, the floor is yours.
Yeah, sure. Yeah, so as Dr. Morrison said, last summer I worked at a company called Pure Storage, which you probably haven't heard of it because it's like a B2B company, so it's not like consumer facing or anything. But just as like a brief like TLDR of like what the company is, it's like a enterprise cloud storage. Just very quickly explaining it. So like working with like a lot of like physical arrays or like more of like a software as a service now sort of thing for companies. But I guess to get there, I worked a lot the summer between my sophomore and my junior year, and then my fall semester of my junior year. I was pretty much constantly on LeetCode and grinding a ton of questions, and which it seems like you guys are doing now, which is super good to do. When I always look back, I wish I started doing a ton of LeetCodes earlier. I honestly just didn't really know how the interview system looked. But also, if I were to give a big plug for anything else, I'd say side projects and open source was a huge help for me. Not just like not necessarily for the company I ended up working, but working in open source projects has helped me get referrals with companies in the past, and also provide like sort of like real world experience closely with and it just kind of shows you're passionate, and super easy talking points. Also, I think companies like people who are pretty into coding, and I like open source a lot. So and I guess going off of that, some other things, I guess I've noticed this is kind of a trend with and if you guys want, I can try to find some resources. A kind of a trend with companies I've noticed specifically around like the Bay Area is occasionally companies like Pure Storage or like a Facebook will ask some operating systems type questions. And I know the way our class schedule is, it kind of comes, operating systems can go as late as spring semester junior year or even into your senior year. So that's something that depending on what you look up for the company, it just might be something you want to keep in your back pocket. Nothing like super intense, but just kind of like knowing what a threat is. And it's okay if you don't know what it is right now, but like, or even if you do in the interview, but that's something I really lucked out, and we learned about threads the week before my interview I had. So that was pretty sweet. But overall, I guess I would say before I guess I open up to questions is I think LeetCoding and not just necessarily grinding through LeetCodes mindlessly, but like going with a purpose and really understanding the backings and the algorithms and data structures behind the questions really helped a ton. And almost like I used to do mock interviews with my friends a lot, because it's a completely different experience doing like an online application or like a hacker rank than it is to doing a I guess this year it'll be like a CoderPad like live on Zoom interview, but it's a completely different experience. And I guess shameless plug, I have some time slots. I think a ton of upperclassmen right now have some time slots to run mock interviews through the Career Center. So I could drop the link to that. But if you guys are looking for extra practice on top of what you guys are doing, that's an opportunity through Decode the Interview. Yeah, I think I guess I covered the overall preparation. I guess just to get an idea of what my work looked like this summer. Obviously, I guess I didn't actually physically go to California. I worked remotely from the South Bend area, so a 3-hour time difference. But it was a pretty like agile development. So like working in like sprints where you'd separate your work into like defined like tasks and working on like 2-week sprints to accomplish the goals. And specifically because of COVID, it was pretty a pretty self-driven summer with me and my partner. And I worked on the cloud organization, and I thought it was a really cool experience getting to work with a bunch of like super new technologies, like working with like Kubernetes and a bunch of other like Redis and a ton of stuff just thrown together. And what was really awesome is at the end of the summer, it's just like, oh yeah, this stuff like started pushing stuff to production and it's getting out there. So I think it was a really rewarding experience. I mean, it was definitely interesting, and honestly, I was a little intimidated going in at first to the company, but it was a pretty great experience. So yeah, I guess if anybody has any questions, I'd love to answer them. I hope I covered what you guys want to hear, but
Okay, does anybody have any questions for Sam?
Yeah, I had a question.
Yeah, go ahead, Luke.
Can you hear me? Okay. So I've applied to a few companies so far, and a few of them have sort of like automated coding challenges they do, that are sort of like through HackerRank or all those different websites. How different are those from the actual coding interviews?
sure. In my mind, I feel like those online like the online HackerRanks, they're really trying to see like if you have like a base level of understanding, like where sure some companies will even say like we won't look at performance, just correctness within certain constraints. But I personally found them to be pretty similar difficulty wise. Sometimes the interview room can actually get a bit more difficult, but the biggest difference I think is you have somebody there with you, or maybe 2 people that you really should be like almost collaborating with and talking to throughout the whole like design. So like typically like you do like out on a whiteboard or something, but like in my experience, I was just like not constantly, but like talking a lot to the interviewer, and like they're usually super helpful because like I mean they sign up to do this. They're not like forced to interview you, but I guess sometimes you'll get thrown in some like trivia questions, I guess, in an interview, like over the phone or something that you won't see on HackerRank. And like by trivia, I mean more like what is this, like describe this data structure, or like name why like NoSQL is like different from SQL or something like that. But most of the time the actual like coding is pretty similar. They're just kind of like I think they're almost looking for in person or like over the phone when you're coding how you think out loud, and like what your thought process is to come to the solution. And the other one is like a bit more base knowledge.
Okay, great. Thank you.
Hey, any other questions? So Sam, I got a question for you.
Sure.
So you were talking about working on independent projects, and the timing of your comment is quite good because they just got assigned their pre-ternship teams, and they're going to be learning about how to drive their own projects. So what I think might be helpful for them to hear is kind of your mindset when you approached an independent project how you kind of worked on things on your own and how you feel that has benefited you as you started to build your skill set.
Sure, yeah. I mean, I was lucky enough, and I'm sure I believe you guys should for the pre-ternships too. I had a partner that I worked with that was awesome. So we collaborated a ton, but I guess my big mindset was I when I couldn't figure something out myself, I would try I would look through documentation to try to figure it out myself. And really, before I started asking questions or raising things up to anybody else, I'd make sure I really understood the problem and mapped out like possible solutions. So when it came time to actually like speak with people about like different design like trait setbacks or other things, it like you basically already have most of the research behind it. And I guess also a huge thing I would say is don't be afraid to collaborate with your teammates. I think that was a huge thing. Like, I mean, we both helped each other a ton this summer, and I think going out of it, I feel like I'm a lot more confident in like if I were to have to run or spin up a service by myself, I think I'd be able to do that now, having done it in the past. And I think having the experience to do it now in the semester is going to be a big confidence booster. If anything, like that'd be awesome. And I guess I'm not exactly sure how closely tied with the pre-ternship is to like the connections. But another thing I would say is honestly, like I was a little not afraid, but like I didn't want to bother my mentor or anybody too much this summer. I would say like a big thing I learned was just not to be afraid to like ask for help or anything, because like everybody's kind of been there, and like there's no real like dumb question when it comes to this stuff.
Yeah, that's another great piece of advice that Sam just gave all of you. You remember that everybody at one time or another coded for the very first time. Everybody in industry at one point had to figure out how a binary search tree was balanced. Everybody had to figure these things out at one time. We all have this, time where we look back on some project that took us 6 hours when we were in school, and that's something we could do in 20 minutes now and go, oh, wow, how did that take me so long? And the reality is the experience and kind of getting over that fear. It's like Sam talked about a couple of times of the intimidation and not being afraid to ask for help or not being afraid to look for extra resources. And that's part of why I'm doing this thing or showing you how to do the emails to the mentors, because kind of getting over that intimidation, being able to say, all right, I'm reaching out to somebody. Oh, I got a positive response. Then you can start doing that again. And that's a great way to create opportunities for yourself as you move on in your career. So that's some really great advice that Sam's given you. So does anybody else have any other questions? All right, Sam, could you do me a favor? Could you drop that link in the chat? And that way I can pass it along involving Decode the interview.
Oh, sure. Yeah. Let me just pull it up. I think it's on the Career Center website, career development website.
Yeah, if you do that, I'll make sure that the students get it and pass it along to the rest of the data structure students as well.
Yeah, sure. I think, okay, here we go. So I'll just add a little bit of a extra explanation on here. So you go to this link and then you want to click industry specific one-on-one counseling. And then from there, it should be the one on, oh, where is that? It's going to be the virtual appointments.
Cool. And so,
then grab.
Yeah, Chase Brown says the Decode the interview team has been super helpful thus far personally. I've connected with one of the student leaders and I'm very excited to use the mock interview feature.
Awesome. Yeah, everybody feel free. I mean, I think most of the people are eager to help because, I mean, the big reason I joined the board there is, I mean, I had a couple upperclassmen that helped me out a ton, and I think everybody's pretty eager, I think, to help out. So feel free to even personally reach out to me if you guys have any questions or anything. I'll drop my email on here.
Okay, well, if no one else has any other questions, then Samuel, thank you so much for making your time for the students. And that I think that this is great, a resource for them. And if they have any questions, I'm sure they'll reach out to you further.
Awesome, yeah.
And
All right.
Catherine Evans and Chase Brown say thank you.
Oh, yeah, you're welcome. Good luck, guys.
Thank you.
All right, bye.
All right. All right, so let me share my screen here. Okay, so we're going to cover 2 questions today. And so here's where all the code is going to be, and the slides, of course, are available on the lecture notes page. So the first question is the merge case sorted lists problem. And something you'll actually notice when you get into these interviews is if they say they want you to do a K number of elements, and we'll see the same thing in lecture tomorrow, oftentimes they're leading you right towards using a heap. And so the reason why is because when you sort, when you put something into a heap, all you're doing is heapifying the element down. You're not sorting the entire heap. All you have to do is maintain the heap. So this means that the heap property is often called log of K. And you can take advantage of this to beat log of N, because log of N, you have to account for all of the elements in the particular data structure. So if you see this merge case sorted lists, we're going to go over one, find the kth largest element in an array, find the k most frequent elements in an array. It's dropping you a major hint that you want to use a max heap or a minimum heap. So the problem states you are given an array of k linked lists. Each linked list is sorted in ascending order. Merge all the linked lists into one sorted linked list and return it. Oh, sorry, I skipped over that. All right, so the first one here, we have 3 sorted lists, and then it returns on the output. And notice how it can accept duplicates. In the explanation here, we have the 3 lists, and it merges them into one sorted list. And so here, what the other thing that LeetCode has done is it's indicated that you could potentially have no lists or one or more empty lists and produce an empty output. So what I did in this solution is I wanted to test the robustness of my approach. So the first thing I did is I generated a random number of lists. So I had a pound define directive where the maximum number of lists is 10, and I can have between 0 and 10 lists. And then between that, a random number of values to put in those lists. So in theory, I could have one list with 40 elements, or I could have 6 lists with 3 elements, which means I would have at least 3 empty linked lists. And furthermore, had each value was a random number. So it would select one of the lists and put in a random number to sort. So this solution has K sorted linked lists involving some sort of number of elements, and we could potentially have 0 or more empty lists. And so here's how I went about this. So we've already created a dynamic array. And in the Creativity Challenge 5, you created your own sorted doubly linked list. And here I'm templating it to integers, and I'm templating the dynamic array to a dynamic array of sorted doubly linked lists. And then I call it case sorted lists. And now to do all this random number generation, I seed the random number generator. And now that we understand W conversion, the time function returns a long unsigned int, but srand demands an unsigned integer. So to do this, you have to cast to unsigned integer to make that work. Now that I've seeded that, I've created a number of lists, which is rand mod max lists, and it's going to be between 0 and 10. And that's going to allow me to be able to go through, and all I'm doing in the loop here is I'm creating a sorted doubly linked list, and then I'm pushing it back onto the dynamic array. So if I don't have any lists, then the length of the number of k is going to be 0. But if it's 10, I'm going to have 10 potential sorted doubly linked lists to be able to insert elements. So now the next thing I do is I get a random number here for num values between 0 and 40. And so this allows me to have a potential 0 to 10 lists, and then I can have 0 to 40 elements to put in that lists. So now what happens is I say if num lists does not equal 0. And the reason I do that if statement is, let's say I have 0 lists, but this random number generator gives me 32. If I don't have any lists to put it in, I don't have any memory to do it. So I have to do a check to make sure that I don't unintentionally try to put anything in there, which will result in a segmentation fault. Otherwise, what's happening is what I do is I iterate through the total number of values that I get. So let's say I get 22. I'm going to loop through that for loop 22 times. And then what I do is I have yet another random number generator called current list. And so the number of lists that's generated is going to be used there. So if I have 6 lists, this random number is going to give me 0 to 5. And this allows me to select the particular linked list that I'm going to put it in. And then finally, I get an integer, which is a random number between 0 and 100. And now I have all the information I need to put the elements into the linked lists. So I have case sorted lists. Current list is the current list that we've randomly generated. And then insert the value that we randomly generated. And because this is a sorted doubly linked list, it's going to automatically sort this particular list for us. So this allows us to come up with a robust test suite to be able to determine if this approach works. And now what I do before I actually go into this algorithm is that I print out all of the lists. I indicate how many lists we have. And then we use the overloaded operator that we wrote in lecture to indicate the sorted order of the lists. And then what I do is I create a doubly linked list. It's not sorted, and I'll explain why in a moment. And then I run this algorithm sort k lists, where I pass the sorted k lists and the number of lists. Although technically, now that I think about it, since it's a dynamic array, it has a size function, I probably didn't even need to do that. And at the end, I print the final result. So the question is, what do I do here? Well, if I have all these sorted lists, the crucial thing is, how fast can I actually sort it? If I have all these lists and I have a different length every single time, the only thing I care about in any given moment is the front of the list. And when I'm putting at the end, the only thing I care about in any given moment is either the biggest or the smallest, depending on which way I'm trying to sort it. So we are familiar with max heap. And so a max heap will have the largest element at the top. So what I can do is I can just go through each of these elements and push all the elements onto the max heap. And so once I'm done with that, I will have the largest element at the top. And what's going to happen is I will pop, and then I'll have the next largest element at the top. And then I'll pop, and it'll keep going. So we have two reasons why this approach is beneficial as opposed to a binary search tree. First, because I'm only trying to make sure that I have the heapified properties, I'm not actually sorting the entire tree. All I'm doing is sorting and getting the element to the top, so it sorts faster. We're starting to learn about balancing mechanisms, and you've learned about AVL trees. So AVL has the drawback of expensive balancing mechanisms, and binary search trees don't have a guaranteed balance. Plus, both of these have to do all of the sorting. So as a result, if we use a max heap and just pop, then all we need to do is ensure that we have all the elements at the end. So what we're going to do is we're going to iterate through the lists. We're going to push each element onto the heap, and then we're going to remove from the front of each list. So we're going to have, let's say we have 7 elements in a list. I'm going to push this element, and then I'm going to pop front. That pop front method allows me to delete in big O of 1 time. So I'm not trying to delete from the end and incurring any potential worst case big O of n penalties. So when we're done, we just pop all the elements off on the heap. And now here's the interesting thing. We can just use a doubly linked list. And since it's a doubly linked list and we have a tail pointer, we wrote this method push back. And push back just puts on to the very end. So if we get the largest element each time, we just push back onto the end, and then we get the next largest element, and so on. So if we push front, if we push front, then I have the largest element, then the next largest element, then the next largest element, the next largest element, which means we are also inserting in big O of 1 time. And we are inserting the elements into the doubly linked list, so we don't need the sorted doubly linked list sorting mechanisms. It's going to be already sorted for us. So this removes a significant amount of time for us to perform these tasks. And so now what I want to show you is the sort K lists algorithm. And I have the number of lists, and then I have the I have the lists itself and the number of lists. So here I call this one by reference because I only want to call a pointer, so we significantly reduce the amount of memory that we need. And I'm passing the number of lists. What I've done next is I've created a maximum heap. And so what I'm doing is first I'm iterating through each of the lists. And then what I'm doing is I say, while k-sorted lists is not empty, I'm going to get the element at the front. So we also presented a front method that gives us the element at the front of the linked list. And then we call pop front to delete. So accessing is big O of 1, and deleting is big O of 1. So once I've done that, all of the elements from all the arrays are now in the maximum heap. So now what I have is I just have a doubly linked list, which I call result. And then while the heap is not empty, I read the top of the heap and I push that onto the front of the doubly linked list. And then I pop from the heap. So accessing is big O of 1, inserting is big O of 1, and then removal is that big O log of k in the worst case. Because we put the element at the back, up to the top, and then heapify it down. And then at the end, once we've done that, we return our result. And so what I would like to do is I'm going to bring this up here. And now I'm going to run the command make sort k lists. And so the first time I run, it randomly generated 2 lists. And here, oh, sorry about that. And then list 1 has a lot of elements, and list 2 has quite a few fewer elements. So randomly it came out like this. And then we run the algorithm, and the sorted list comes out completely sorted, even though it's a doubly linked list that doesn't have a sorting mechanism. Now, if I run sort k lists again, okay, so that time it was 2 again, and it sorted everything. We had a large number here. I'm going to keep running this until it randomly generates a duplicate. Huh. Oh, there we go. So that's what I mean by a duplicate. So here we had 1 list, and it sorted, and it worked fine. Let me run this again. 0 lists to sort. The list is empty, so that part of the algorithm worked. Here we have 6 lists, and we have all these elements here. All of them are sorted in the sorted doubly linked list. And then our final doubly linked list that's doesn't have a sorting mechanism has all of these. So you can just keep running this. This is another scenario I wanted to show you. We had 7 lists to sort, of which 2 of them are empty. And that's perfectly fine. We were able to get all those elements and sort them onto the heap. And we can just keep testing it, and we have a robust test suite, and we can see that we're able to account for duplicates, 1 or more empty lists if we don't have a list at all, or if we have, in this scenario, we have 9 lists to sort, and we got all 40 to put in. So we have counted for all of this. So we've met this k sorted lists requirement. All right, so before I move on, does anybody have any questions?
I have a quick question.
Sure.
So this is O log of k, correct?
Mhm.
How does it not become O log of n because of the first the nested while loop that's inside that for loop for when you're pushing every single element from the list onto the heap?
So I'm talking specifically about putting the elements into the heap.
Oh, okay. So
Right.
just like that final sorting function is
Yeah. So
okay.
in that case, that last stage would be n because we have that. But even then, it's like a worst case big O n log n, right?
Okay. Yeah. Okay. Thank you.
You're welcome. All right, are there any other questions? Oh, sorry about that. All right, so let's go to problem number 2. Okay, so here's several other test cases that I've run. So the second problem is that we're going to find the median from a data stream. The problem states the median is the middle value of an ordered integer list. If the size of the list is even, there is no middle value. So the median is the mean of the 2 middle values. So here in this case, it's odd. So the median is 3. But in this case, it's even. So it's 2 plus 3 divided by 2, which comes out to 2.5. So the interesting thing about this problem are these 2 constraints. We have to design a program that can add an integer from the data stream to this data structure. And then we want to return the median of all the elements so far. And this is a crucial part. Because if we're saying we want to return this at any given moment, ideally we want to be able to do this in big O of 1. So we have to be able to access everything. And we have to have it at the top. So this means that a binary search tree or anything like this is going to be right out, because the top of the tree is going to be what gives us the most balance depending on our balancing mechanisms. It's not going to be the median. If we have an array, then the interesting thing is we can access it in big O of 1, but then it involves how do we sort? And when we sort, we have determined quick sort, which you all wrote in a creativity challenge, and that gives us that big O of n log of n sorting. The issue is every single time I insert, I then have to go into this n log n sorting. So it's log n for every insertion, and then we have to account for n here. The thing is that all I want is to get the median to the top somehow. I want to be able to access it in big O of 1. So some things we could think about are terms of stacks or queues or priority queues. And we've learned about priority queue using a sorted doubly linked list so far. In Friday's lecture, we are going to learn about using a minimum heap to implement a priority queue. So the thing with the heaps is, this is where this log of k comes into play. How can we just make sure that whatever we have at the top is good enough? And this will kind of answer Chase's question in more detail. And so here's this, what I'm talking about. Can we beat big O of n log n? And here's how we know this. We know that the median splits the elements in half. And we only really care about reading those elements and calculating the values. So we have to think about what our possible cases could be. We could potentially have both halves be empty. We could have one element, 2 elements, 3 elements, 4 elements. So we could have either both halves are equal in size, in which case we have to read both and add them and divide by 2, or the other scenario where 1/2 is larger by 1. And so here I have a set of insertions. And what I want to do is kind of show you how the median would go. And from there, you might be able to see the pattern. So initially I did 10, and I put 10 on the left, and we just say that median is 10. So now I'm going to put in 7. So my result should be 7 and 10, which means I would want 7 over here and 10 over there. So we're starting to see some, if we have a condition, we want to pop and push, and then pop onto the other list. So we're going to see that 7's going to go onto the left and 10's going to go onto the right. And then we add and divide by 2, that gives us a median of 8.5. So now I want to put in 6. And if we have 6, I can say 6, 7, and 10. And so now I can say, well, I want 6 and 7 over here and 10 over here. And specifically, I want to be able to access 7 because that is the new median. The next one I want to do is 5. So if we have 5, 6, 7, and 10, we want to somehow split these up and be able to access 6 and 7 simultaneously. So what's going to happen is I want to move these elements over. I want to move 7 over. So let me go back, show you. I want to move 7 over. And then I want 6 to be at the top of this pile. And then we add those together and we do 7 plus 6 divided by 2 gives us 6.5. We keep going, we do 11. Well, 11 should be on the right-hand side. And so now what's going to happen is we're going to see that 7's going to move back. And so if this number is greater than the right, then we're going to move that back over and then put 11 in this pile. And then since they're uneven, this left one now matches the median. So now what I'm going to do is I'm going to do 12. I'm going to move 12 here. I'm going to see that 10's going to move up. And now we do 7 plus 10 again. So that gives us going to give us the median of 8.5. And so the other thing I want you to notice, and this is a little hint, is that I have 7, 5, and 6 here. It's not sorted. If I were to sort it, it would be 7, 6, and 5. But I don't need 6 and 5 sorted. I just need them to be less than 7. And so now you can see where the heap comes in to benefit us. So when I put that in there, now we have the median again. I put in 13. So 13 is bigger than 10. So we're going to see 10 move over to the left. And now 10 is the median. And now what I'm going to do is I'm going to put 3 in. And so since 3 is less than 10, you're going to see 10 move back over here. 7 is going to be at the top. And again, we're going to get a median of 8.5. Okay. So the pattern is that if they're both empty, we just want to initially push on to the left. Then we want to evaluate the case where left has more than right. So in this case, there's 2 possible things that could happen. If the value we're inserting is less than or equal to what's on the top of the left, then we want to take that value on the top of the left and move it over to the right, pop that value off the top, and then take that new value and put it on the left, which will give us an even value. Otherwise, if it's larger, we just push that onto the top of the next heap, and that'll ensure that we have 2 evenly sized piles. Now, if the piles are even, then we have a scenario where if the input is less than or equal to the right pile, then it's simple. We just put the element on the left. Otherwise, if it's greater than what's on the top of the right pile, then we need to move that element over to the left and then push that in there. And then again, we have our balanced. So we have a scenario where either they're balanced or the left is going to be larger by 1. Which means when we actually have to make the comparison, if the left pile is greater, then we just read what's on top of the heap, and that's our median. If they're equal in size, we read what's on top of both of the heaps, add them together, divide by 2, and that's going to be our median. And now that we have this set up, we have guaranteed there's never going to be a case where the right has more elements. Right, so on the left, we're going to use what we've learned already in class as a max heap. On the right, we're going to discuss what we learned, we're going to learn in lecture on Friday, which is a minimum heap, which just is the maximum heap, except the heapify is in the opposite direction. So this will ensure that the top of the left will have the largest of the left half, and the top of the right will have the smallest of the right half, which is precisely what we want for the median calculation. So furthermore, we only heapify the latest element, and there's no need to sort beyond that, which makes our solution faster than quicksort. So here, first let me show you my algorithmic approach for, sorry, let me move this over here. So first let me show you my algorithmic approach. Okay, we have nothing in the chat. Let me show you my algorithmic approach to inputting with a max heap left and a minimum heap on the right. So first, just like we did in the description, if they are both empty, then I'm just going to push it onto the left heap. Otherwise, if the left size is greater than the right size, then I have those 2 scenarios. I check to see if the element on and the input is less than or equal to what's on the top of the left. If that's the case, I want to move what's on top of the left over to the right. So I have right dot push, and then I read what's on top of the left. So now I temporarily have a duplicate. So then I remove what's on top of the left, and then I push that input onto the left side. Otherwise, if the input's greater and they're not even, we can just even out by pushing this element onto the minimum heap. The other case is what happens when they are equal sized. And so if they're equal sized, then what's going to happen is if the input is less than or equal to what's on the right heap, then I just want to push it onto the left. Otherwise, if the input is greater than what's on top of the right, then I need to take what's on top of the right and move it over and then push it input onto the right. So here I have left push, I'm getting the right top, and then I pop the right off of the top, and then I push the right with the input. In order to get the median, first I have the case where if left and right are both empty, I just print out no values that are input and no median to calculate. Otherwise, if left size is greater than right size, and we've set this up where the left size will be either equal or greater by 1. So if it's greater, that means the element on the top is the median. So we can just do it in big O of 1. And then otherwise what I need to do, since it's an int, I'm going to cast a double. And then I say left dot top plus right dot top divided by 2. And the reason I have to do this, let's say the left is 2 and the right is 3. If I leave those as ints, that becomes 3 plus 2 is equal to 5 divided by 2. If it's a double, it's going to correctly give me 2.5. But if it's integer, it'll return 2. So this ensures that we return the absolute correct data. So now in main, what I've done is I've created a min heap and a maximum heap. Then I say, well, while inputs greater than or equal to 0, so I'm prompting the user to say to enter a positive integer or -1 to quit. Then I read in cin, and then if input's greater than or equal to 0, I add the number using the algorithm, and then I'm going to print out left heap and then a tab and then the right heap, and then I'm going to get the median and print the median to the user. So we can see that after every insertion that I do, we are able to get the correct median. So on the slides, I have several cases. So what I'd like to do here is make clean, clear, and then it's make find median. And we can work through this and see the result. So first I want to do is I'm going to go over the example from the slide just to show you step by step how everything works. So I want to insert 10. We see that the left heap has 10 and the right heap doesn't have anything. And so what I'm doing is I have a method where I'm printing the dynamic array inside of the heap. So now I want to insert 7, and we're going to see that 7's now on the left and 10's on the right, and I correctly print out the result of 8.5. So when I do 6, we now see that 6 is on the left and 10's on the right. And when I do 5, we're now going to see, well, first of all, when it's uneven, this is 2 and this is 1, that means that we're just going to read the top and we get 7. For here, we have 6, 5, 7, and 10, and we have a median of 6.5, because 6 plus 7 divided by 2 is going to be 6.5. When I add 11, we're now going to see that 7, 5, and 6 is on the left. So we're heapifying. We don't need to keep 6 and 5 in that order, just as long as it maintains the heap property, because the heap actually looks like this. So we have 10 and 11, and since this is bigger, 3 versus 2. So here I'm printing the length of each of these. So that means we just get it off the top. So I have 7, 6, and 5. I had 11, I'm sorry, I put in 11. Then I put in 12, and we correctly calculate 8.5. Then we had 13. And we see we have 4 and 3 as our lengths, and 10 is the largest element, so the median is 10. And then I'll do 3 on the right, and we're back to a median of 8.5. And then I can quit with a -1. So if I run executable find median, and I can just do 100, 99, 98, 97, 34, 22, 16, 87, 104, 2, 29, 6. And we can see that the median is changing every single time. And no matter what, we never have a scenario where left or right or the left heap is more than 1 greater than the right heap. And in the slides, I also have a few examples here. Oh yeah, so another one, worst case scenario, 7, 7, 7, 7, 7, 7, 7. We see that it's still working correctly no matter how much I screw it up. All right, so does anybody have any questions about my approach to that problem? Okay, well, in that case, that is the end of the optional lecture. Thank you for coming out. I hope that Sam gave some really great advice, and I hope you learned a lot, and I will see you all in lecture tomorrow. Hey, you're welcome, Chase. You're welcome, Catherine. You're welcome, Fat Kong.